Welcome guys, let's do some physics. Alright, so the first thing I'm doing is I'm kind of coloring in to show, hey, you have two piles of dirt equal size, put them on top, what do you get? Big pile of dirt. But that big pile of dirt is really kind of like both of these added up together, so it's both their amplitudes added. This is called constructive interference. Now, we have an equally sized pile of dirt in a hole. Obviously, put them together, you get nothing. There's no energy, no amplitude, so it's a straight line. But if you kind of looked at it, it really would be like a down and an up part, but they just cancel out, leaving just flat. Big hole, small pile of dirt. Put them together, what do you get? Smaller hole. Now in reality, it's actually a big hole with some of the dirt piled in. You can see there, it's the original one, and a little bit, so part of them cancel out. And finally, you have this weird function. Obviously, when you get it, you're just going to kind of take off a little bit of the chunks. So you know, with that little bit right there. Cool. Next up, now we have this cute little picture with the frequency of 12. And you see a couple numbers there. So I know 12 is the frequency in hertz. Now, the amplitude is kind of like that right there. So if the total is 20, the amplitude's got to be 10 centimeters, aka 0.1 meters. And 20 is from that point, but I know that a full wave is from that point to that point, you see there. So what I have is half a wave, so a full wavelength would be double what's given, which would be 24 centimeters or 0.24 meters. To find period, period's 1 over frequency. The frequency is 12, so it's be 1/12 in seconds. And finally, one harmonic is a single pulse. So here I see 1, 2, 3 pulses. So this is the third harmonic. Next up, I have a question down below there. So now I would think, oh, I have frequency is 1 over period, so it's be 1 over 0.5, but that's not correct. Since 0.5 is not the time for one wave, it's the time you're making this wave. So you can have a lot of different pulses made during that 0.5 seconds. I'm going to do V equals F lambda. F is frequency, lambda is wavelength. I'm given the speed, I don't know the frequency, but I'm given a wavelength. And I find 471.4 hertz. Now let's look at the back. A guitar string is 0.75 meters long. Okay, I'm going to draw that in. The waves are going at a certain speed. Find the frequencies of the first three harmonics. Okay, so the first harmonic is just one hump. Looks like that. But then if you played harder, the second harmonic would be 2 humps, or a full wave. You see it right there. 3 harmonics would be, this kind of picture from before, 3 humps. So for the first harmonic, that's half a wave there. And half a wave is on 0.75 meters. So therefore the wavelength would be 1.5, or double that distance. Even my categories. For the second harmonic, 0.75 meters is a full wave. For the third harmonic, you get 1.5 or 3/2 of a wave on that. You could solve for the wavelength. But it's a simple way of doing this. I'm going to use V equals F lambda. The velocity is 180. The frequency I'm trying to find, but the wavelength is 1.5. And I find it to be 120. So the next one's got to be 240. Next one's got to be 360.